Good afternoon. Sorry for the slight delay there. I was having fun getting my cursor to to unmute my audio. My name is Roger, and I am pleased to meet the 18 participants we have this afternoon. I'm hoping that you'll find this topic as interesting as I did when I first started looking at it. I'm an electrical engineer, work in photovoltaics, and had never really looked into the gory details of what's out there. I mean, I knew that we had a public service commission in Florida, and utilities are regulated, and there's transmission lines and distribution lines and stuff like that. But there's a lot of stuff I wasn't aware of until I read through this material, and I think, well, it had quite an interesting effect on me, and I hope that we'll find this to be an interesting afternoon. There's a lot of stuff obvious, a lot of stuff not quite so obvious. So let's move on here. And what I'd like to do is if you have a question, let's use the participant box and the raise hand function in the chat. We'll reserve for our host if he has any messages for us, or if you have any questions relating to the technicalities of the presentation, please put them on the chat box. So otherwise, I will be watching my participant box for any indication of hands being raised. And if you raise your hand and if I don't respond to it, please feel free to open your mic and just say, hey, Roger, I have a question, and we'll deal with it. All right. The whole idea is for this to be interactive, and I want everybody get as much out as you'd like to be able to get out of it. So here we go. Like give credit, one might think that if it's based on something done in 2012, that it must be pretty much out of date. And what's interesting is what we're looking at is how the predictions of 2012 are coming out now as of 2024, 25. So this is a pretty interesting study. It has a number of different volumes, and the National Renewable Energy Labs are pretty well known for having some pretty credible material that they issue. So this is the basis of it, but we've done our best to update to the extent possible. And some of the things are just not all that easy to update. Sometimes you're a year or so behind because they're trying to count things in a lot of different places. Okay, so here's what we want to do. Well, I guess we're doing the introduction right now. I'll look at photovoltaic systems, wind systems, what happens with these variable sources to the grid, and I think that'll be pretty obvious. How do we overcome this? And so that's just where we are. Once upon a time, photovoltaics was kind of a hobby. Back in 1970, we were paying about $100 a watt for photovoltaics. That's no longer the case. In the United States in 2020, 3.1 gigawatts of residential PV were installed. This is a little out of date. A whole lot more were installed in 21, 22, 23, and 24, but compared to 3.1 gigawatts is quite a bit. We'll see some graphs in a minute. And 16.57 gigawatts was installed in the United States. So therefore, 3.1 of residential was about 20% of that. The other 80% goes into commercial and utility. Globally in 2020, and this is just before the pandemic, 107 gigawatts were added. And so this just kind of puts how does the United States compare with the rest of the world, and you can see where something like 15% of all the photovoltaics are here in the United States. But it's not that nobody else is doing anything, because the rest of the world is also doing quite a bit. China, for that matter, in fact, installed 48.2 gigawatts in 2020, which was almost 3 times what we did here in the United States. And India did 3.2. And all three of us, the United States, India, China, and for that matter, the rest of the world have continued to increase their installation. So in other words, these variable sources we're talking about are becoming more and more and more all over. A lot of jobs, a lot of work, efficiency of the systems continues to improve, the reliability continues to improve, warranties get better and better. Even now, like things like microinverters, electronic components are coming out with 25-year warranties, as well as the modules themselves. So 25-year warranty means you want to install them so they'll last and stay there for 25 years, including not blow away or get rusty. So that is an interesting challenge, but it is being met on a daily basis. And the cost keeps coming down, which means that Wall Street is interested because the economics now of solar are really, really good. And we'll look at some comparisons just to show why these things are happening. And it's mostly, I like to think that people are doing it because they think it's important and the right thing to do. But fact of the matter is, it is very economically feasible at this point. And I think that's the primary driving force. If we look at the cost of photovoltaic modules per watt historically, we'll see through back in 75, they were over $100 a watt. In 2015, they were down to about 60 cents a watt. And as we move out in 2020, we're down to 30 cents a watt. And that has remained about steady for the last few years. It hasn't dropped a whole lot more since then. But it hasn't gone up either. So if we look at the shipments, we see here up through 2030 that through 2016 was less than 100 megawatts. But now, as we move up to 2021, we're now at 10 to the 4 megawatts. Well, 10 to the 4 megawatts is 10 gigawatts. 10 to the 5 megawatts is 100 gigawatts, and we're rapidly approaching that terawatt range. And so within these two boundaries that might have been estimated or predicted from back in the 2010 timeframe and 2012 timeframe of the study, you can see that indeed the actual shipment of PV worldwide is within what one would have predicted back in 2012. So the prediction is looking okay. In 2021, it was about $3 a watt to do a residential installation. And the utility installation cost in 2021 was about $1 a watt. And the asterisk means we're talking about before the investment tax credit. Now, I saw a flash that there are two things in the chat, and I'm wondering if we had a okay, that is relating to audio problems. My mic is on, and the little green thing is saying that I'm talking, so hopefully we're not having audio problems. I did talk with the host at the beginning to verify that. So hopefully everyone else is hearing okay. There's also a closed caption available if there's an audio problem. You might want to try the closed caption. Okay, so we can see we're on track for getting up to the 10 to the 6 megawatts, which is 1,000,000 megawatts, which is a terawatt. And that looks like that could happen somewhere between now and close to 2030. Now, if we look at the growth of sources worldwide of all kinds of primary energy sources, like solar, like nuclear, like hydroelectric, coal, oil, natural gas, you can see the results here on this chart. And through 2021, you see that, or through 2020, you see that the numbers are up to, um, somewhere over 100 quads. And you notice that as the consumption of petroleum went down a little bit in 2020 because of the pandemic, and then it started bouncing around. And these numbers are about 2 years out, and what we've observed is that if we do add that additional data, the natural gas consumption has continued to increase a bit as utilities are replacing coal with natural gas. Petroleum has kind of leveled off, but coal has been on the way down. Okay, so notice the diamond shapes in there. Those are on their way down because a lot of the coal that's being used worldwide is now being replaced by natural gas and or um, renewables. So as you see the growth of the various other sources, the green, the blue, dark green, light green, and the blue down below, that the wind and photovoltaics, the starred green line, is growing most rapidly. And at the present growth rate, it looks like by about 2028, it's very likely that we may hit the 100 quad mark. The hydro, which is represented by the little pentagon house-like things, looks kind of level. On the other hand, if you look at what's going on in China, China is building a lot of hydro, so that probably is actually going to go up a bit. And the nuclear has remained relatively level, the blue line. Not very many new nuclear are being built, and the reason is strictly economics. The cost now to build a new nuclear plant is a whole lot more than building any of the other conventional sources or renewable sources for that matter. So just some numbers because this kind of background provides reasons why what we see happening in terms of growth of renewables, why it's happening. It's happening because they are less expensive and to some extent because they are, say, greener and more environmentally friendly. But for the most part, it's an economic issue. This is energy. This is kilowatt hours that are being produced, and this is kilowatt hours of source energy. So given that you only get about a 35% return on investment if you burn a renewable resource to get electricity, whether it be coal or whether it be natural gas, it takes 3 times, roughly a factor of 3 more of primary energy to get electrical energy. And if you're just using the heat energy, then that's great. But if you're burning the primary source to get electricity, then your return on investment is not all that good, less than 40% generally. Okay, so in any case, notice not 2019 is where the magic number where the renewables passed the nuclear worldwide production. Um, Back in 2020, nobody would have expected that to happen. Well, some people, optimists, maybe would have. Okay, so let's move on, see what we got. What about photovoltaic themselves? So what about new developments and so forth? Well, if you go to this chart by the National Renewable Energy Labs, for one thing, you get almost dizzy because there is so much going on. But there's some interesting things. And if you just look at the little orange line with the yellow dots in the middle of the circles, that's perovskite. And notice that this wasn't even on the map until 2013. And this technology is now about to be put into, and you can see the graph goes up to 2022, and the perovskite technology is now, they've figured out a way of stabilizing it. That was a problem up until now, and they figured out a way of mixing it with silicon, into a multi-layer cell that is significantly more efficient than the run-of-the-mill silicon cell. Notice the efficiency there is up in the 26% range. And so that's something to watch out for. This bottom line is stay tuned because there's a lot going on and things are continuing to improve as people are excited about the various technologies and they're working hard to improve them and make them even better. Okay, let's talk a little bit about sun, a little bit about the wind because it helps to know. Now, it's pretty well known that the sun comes out during the day and goes out at night, and therefore photovoltaics don't work real well at night. So obviously we need to do something about it. But how much sun is available? How much energy? How much? What's it take anyway? So the peak sun intensity is about 1,000 watts per square meter. Okay, that's when it's overhead, shining straight down. So that doesn't happen too much. But then again, if it's overhead shining straight down at the equator, or if you have a high mountain at the equator, like somewhere like, for example, in the capital of Ecuador at 9,000 feet, peak sun intensity can be pretty intense when the sun is overhead at the equinoxes. So because there's less atmosphere that it has to go through. So depending on the technology, you can convert about 22% of this 1,000 watts per square meter into electricity. If you do it the low-tech way, you can do 40% or so if you have some real high-tech, very expensive technology that is sometimes used in outer space. But for use here on the surface of the planet, most of the technology is silicon. That's about 96% of all that's out there is crystalline silicon now. And the best of the crystalline silicon conversion is around 22%. So that means that it's possible to convert about 1,000 to 2,200 kilowatt hours a year for every kilowatt of system that is deployed, depending on where it's located and what direction it's looking. Is it on a south-facing roof tilted at latitude? Is it on a west-facing roof? Northwest, southeast, what direction? But the National Renewable Energy Labs have very good simulation programs that will tell you on an 8,760 hour per year estimate about what you can expect on average any hour of any day during the year at any location. So it's relatively reliable to do simulations with the technology to guess about what you're going to make. Very sophisticated models out there. They account for all kinds of things, including the equipment, the efficiency of the equipment. So in the case of photovoltaics, the output energy is proportional to the intensity of the sunlight that shines on the collector. So 1,000 watts per square meter gives you one output. 100 watts per square meter gives you about roughly 1/10 of that. So what about the wind? What does that do? Well, it blows, okay. And we know about 85,000 people were employed in 2022 in the United States, 97.5 gigawatts in 2021 in the and worldwide. And here's a few more numbers for you. And by the way, our hosts will be more than happy to share these slides with you on a PDF set. If you want to look at these numbers more carefully afterwards, feel free to request a set of the slides. We'll be happy to send them to you. So I'll be going through the numbers here and the words relatively quickly, just to make sure we get through on time and have plenty to have time to discuss, have questions, whatever. Okay. The small wind turbine thing, 2014. Uh, Try looking it up. Ask your phone, ask something, how many small wind turbines are out there cumulative worldwide. Um, I may not be very that good at looking stuff up, but I tried for about a half hour to get a better number recently, and they kept trying to want to sell me stuff, and I had finally had to settle with this. I'm guessing by 2024, we have a whole lot more than 945,000 small wind turbines out there. But in any case, the big ones are the ones that are really cranking out the electricity. And you notice that a large wind turbine is more or less comparable in its production per kilowatt of deployment with photovoltaics in the desert. And that would be in the desert with a tracking collector. Construction costs of wind is somewhere in the neighborhood of $1.50 to $2 a watt. And the only problem here with wind is that the best performance requires sustained winds. You can imagine the bearings in a wind turbine really don't like gusty winds a whole lot. And the other thing is that the force is proportional to the square of the velocity of the wind. And of course, then the power is force times velocity. So you're looking like output power being proportional to the cube of the velocity. And of course, the velocity of the blades is perpendicular to the velocity of the wind. So you've got a little conversion there, but still, when you add it all up, it comes out as an attractive investment. Otherwise, they wouldn't be out there. Um, Here's what's happening worldwide in wind power. Um, and 10 top countries in doing worldwide wind action are China, United States, Germany, India, Spain, United Kingdom. Okay, so China's ahead of us in PV and in wind, but they've got more people, whatever. I suppose one could argue their government is run by engineers mostly. Um, Maybe they like solar. In any case, China is ahead of us, so if we're going to try to catch up to them, we got a ways to go. We talked about the cost effectiveness of wind, that if we were to put some in my backyard, its cost effectiveness would be not nearly as good as it is on the Buffalo Ridge in Minnesota or certain areas in California, West Texas, and other regions have a lot of wind, like off the coast of Costa Rica, for example. In any case, PV is generally useful almost everywhere. You can get your money's worth by installing it, whereas wind is a little more fussy about where it's installed in order to pay for itself. But there's plenty of areas available for using wind to make a lot of electricity. And Wikipedia is a source of where this information comes from. There are other sources as well. The measure of cost, and here's the economic measure, is the levelized cost of electricity, or some call it the levelized cost of energy if we're talking about other energy forms. And let's just take a look at a comparison here. Natural gas, 7.1 cents a kilowatt hour to make electricity with natural gas. 9 cents a kilowatt hour with advanced nuclear. 4 cents with onshore wind. 4.3 cents with photovoltaics. 4 cents with hydro. And this is from the International Energy Administration in 2020. Those are their numbers. Now, the levelized cost of electricity, how's it calculated? Well, what you do is you add up all of your construction, operating, fuel, maintenance, and decommissioning costs, and you divide them with the total kilowatt hours produced over the lifetime of the system, and that gives you the dollars per kilowatt hour that you have to collect in order to get your money back. Now it gets a little different if you throw in the time value of money and so forth, but that's basically the formula. And so these things are based on assumptions. The part of it is the amount of electricity generated. And for example, a peaking electrical generation source only runs maybe 3 hours a day and not necessarily even every day. So therefore, in order to get the investment back from this kind of a source, uh, it's necessary to charge a fair amount of money for the electricity this source produces. And this is where your peaking electricity cost comes in, because in order to produce peaking electricity, the sources that produce that peaking electricity are oftentimes only run during peaking time, and therefore you have to charge a whole lot more for the electricity, and whether it's for the fuel, the jet fuel, for a turbine type, or whatever. So in any case, this is just a rough estimate. If we take a look a little bit closer, where is my I'm missing something on that slide. It didn't come in what's happening in 2022. Anyway, I don't know where that went. The numbers were lower for in 2022. The numbers were lower for the wind and the solar, and they were a little bit higher for nuclear, and they were about the same for the other sources. Now, the basic challenge of the grid is to make sure everybody gets their electricity when they want it, and that is wherein lies the challenge. Okay, something over here. Let me just check here. Oh, there's a Q&A. Let's take a look. Where's coal on the LCOE slide? You know what? Bruce, I don't know. I think it's somewhere, and of course, oil is missing there as well. And the reason else the coal is not on the LCOE slide is because utilities are moving away from it. And for a number of reasons, and one of the reasons is cost, but the other one is they're trying to reduce their carbon dioxide emissions. So I don't know the answer to that, but you can check the source of the numbers. In fact, I think if you would just Google what is the levelized cost of energy for coal, you might be able to get an answer on that. And that's a good question. Now you've got me curious. I want to look that up myself. Um, I'm not sure what it is. Just don't know. All I know is that people are trying to move away from coal. The Americans are trying to move away. The Chinese are trying to move away. Everybody's trying to move away from coal because it's generally considered less desirable. And mostly it's a pollution issue. Coal, the smoke out of coal-fired plants is not particularly pleasant. And of course, there's also the CO2 issue. We're talking about coal being the heaviest emitter of carbon dioxide because coal is basically carbon. And so you mix carbon with oxygen to get CO2. And so 12 units of coal gives you 44 units of CO2. And it's pretty heavy duty, and they're trying to get away. And that's the best I can do for the LCOE on coal. It simply wasn't in the collection of numbers that I looked for. Okay, let's see, where am I? Okay, so we want to supply load to the loads. And the base load, everybody knows what that is. It's as low as it goes for the day, and that's generally at night. And that's kind of what nuclears are all about, because back long ago when they started building a lot of nuclear energy, um, they like to run at a constant output because they are not very stable. And to get them to run at a stable equilibrium point, you want to get them cranked out to a constant output level. And then you want to keep it there. So they built a lot of these pumped hydro storage facilities back 50, 60 years ago to pump water uphill at night to use up that excess nuclear. And then they were able to let that water run downhill, turn the generator around, or turn the system around and generate electricity with the return from what they pumped up. So it's kind of like a big battery, roughly 80, 85%, maybe about 15% loss in the process. But it was still better than trying to crank down the nuclear at night and crank it back up again. Once they get it going constant, they want to keep it there. So the total load is the base load plus the variable load, and I think everybody knows that. Some loads very slowly and others very quickly. I mean, if I turn on my water heater, it starts pretty fast, or if I turn on my oven, it comes up pretty fast. But then again, there's some things that vary slowly. So in any case, the more loads that are connected, the more steady the demand. And one illustration of that is simply if you look at how do you size the service for a large residential building, and you'll see that they have demand factors. So that if you got 50 units in that building, the demand is down to about 30% of what it would be if you had 50 of them all by themselves. And of course, that applies to a neighborhood as well. Because not everybody runs their stove at the same time, not everybody runs their air conditioning at the same time, not everybody runs their water heater at the same time, and so on and so forth. So the more loads that are connected, it tends to level out the demand a bit. And just as loads can vary slowly, the sources can change output quickly, but others are kind of slow to respond. So these are all things that one needs to think about when trying to deal with the idea that variable sources are kind of unpredictable, a lot less predictable than the nuclear and fossil sources that we've been accustomed to, or hydro for that matter. So therefore, we have to have stuff that turns on fast in the generation mix, and we're going to look at how do you do that. It's also been demonstrated that distributed renewables can affect substation equipment. So if you got a lot of solar out there and you start putting more electricity back into the distribution system than people need, then it starts going back towards the substation, and this becomes, as opposed to a distribution system, it becomes a transmission system at distribution voltages. So, and that's going to affect the equipment at the substation. So that needs to be thought about in the process of managing these variable sources. Now, what does a grid entail? Well, it's got a lot of stuff. You got fuel, resources, lots of ways of making electricity, distribution, transmission lines, loads. Of course, without loads, they wouldn't need the rest of it. There are networks and there are measurements and there are information control systems. There are virtual networks of money and business relationships. And guess what? There's the regulators out there. So there's a whole lot of sort of invisible parts here. It's not just burning the coal, oil, or whatever way we're going to make that electricity, but there are folks who are involved in deciding how that's supposed to be done. And not just folks, but a lot of instrumentation and control systems that also get involved in the process. And of course, the process is getting presumably smarter all the time in terms of all of its artificial intelligence that's being introduced. So in general, though we can acknowledge that the grid requires real and reactive power. Okay, and well, reactive power is simply power that would run a motor, for example, because motors have magnets and means the reactive power is out of phase with the real power by 90 degrees, and it doesn't really do any work. It's the real power that does real work. But sometimes you can't get the real power without having some reactive power involved as well. And as a result, the generating sources need to be able to supply both real and reactive power. And because of both components, the grid itself tends to behave like an RLC circuit for the electrical engineers or a mass spring dashpot circuit for the mechanical engineers. And usually the grid is overdamped, meaning that it's pretty stable. You do something to instantaneously, for example, and it will cause a momentary glitch in the grid, over voltage, under voltage or something, but it relatively rapidly recovers. But when the load goes down, that's what damps the circuit. So under low load conditions, the grid can become underdamped. So that's just like when your shock absorbers go bad and you press down on your car. Let's see, I saw my screen come on, but I don't see questions. Okay. But so when there's not much of a load on the grid, it's like you've got bad shock absorbers, and then you press down on the on the hood of the car, and the car bounces up and down a little bit rather than just goes down and comes back up slowly. So there are lots of computer programs that model the performance of the grid, and when you want to put a big PV system on, you generally do a grid study to see how the grid is going to react to this PV system. If, for example, a big cloud comes over the PV system and it drops out fairly quickly, what's that going to do to the stability of the grid? So it's not necessarily just the providing the power, but providing it without creating any kind of an unstable position or situation due to things happening too fast. So that's part of the challenge here. Sources generally tend to ramp on and to ramp off, start up relatively slowly. Even solar inverters are oftentimes programmed and designed such that they don't turn on instantaneously. It takes them a little while to turn on. My chat thing just, when I'm presenting, my screen is filled with the slide except when something happens. And what I'm not sure about is whether I don't see any indication. Is there any questions? If you do have a question and I don't see it, again, I remind you, open up your mic and just break in, okay? Right now I see 3 things in the chat box, but chat box is for communicating with the host. Let's just be sure. Yeah, there we go. Type the Q in the Q&A. Okay. So large renewable sources are generally designed to not be a step function excitation, to generally turn on and off in a matter of a second or two. Not that they can't do better than that if there is reason for it, and we'll talk about that in a little while. So modeling the grid responses, like modeling any second order differential equation, essentially. And if you got a ramp function or whatever, and this is basically what the modeling programs try to do. And like we said, sometimes if you ramp too fast, it can lead to grid instability, so you need to watch for that. Okay, the result is that you need to smooth out rapid changes, okay, and there are ways to do that. And something that's slightly less obvious is that generators are not designed to absorb power. So if you have a rotating generator and you try to run electricity back into it, it's going to pretend that means you're trying to turn it into a motor. And the prime mover is not happy about that. So that's another thing we need to be careful of. We don't want to generate so much power that it creates a situation where the generator itself is where the renewable power, for example, is trying to run the generator backwards. We got to do something to that renewable power so that doesn't happen. So if the wind or PV tries to feed power into the generator, okay, that's what we just said. So we need to be careful for that. Now, NREL studied all these concerns back in 2012, and here's what they decided. They said, we can fix it. We've got the technology. And in fact, by 2050, we can supply 80% of total United States electricity and meet the demand on an hourly basis everywhere. So that was pretty reassuring. And now, the only problem with what they said about this 80% is it now appears that we can supply 100% by 2040 because of the rapid growth of the technology. And we can still probably provide 100% by 2040. And we have all the technology necessary to deal with the fluctuating output of wind and solar. So that's the 2025 version of the 80% prediction back in 2012, is that that was conservative. We can probably do a whole lot better. We're doing 20%, a little over 20% right now. So obviously that means there are going to be some leftovers that has to be provided by something else. And that's anybody's guess what that might be. But my guess would be nuclear, but then there's hydrogen, there's other things coming online. So, and of course, storage, that's another thing that doesn't exactly provide, that doesn't generate electricity. It stores it and it gives it back when you want it. And that's really important. So how do we achieve this 80% goal? And I'm going to call it 100% goal now because we all now know that we can do 100%. First of all, we need more flexible conventional generation, lots of grid storage, new transmission, and then for grid storage, is it cost effective? And the answer to that is yes. And that's covered in a more lengthy presentation that shows why it is. But some new transmission to move energy, for example, from the desert where the sun likes to make lots of electricity to places where it's used, and maybe from west to east, so that when it's generated at 2 o'clock in the west, it could be used at 5 o'clock in the east when they really need it, if we have more east-west transmission. Loads themselves can be made more responsive, and that's happening as we speak, called load management. Turn loads off if you don't need them. That could be swimming pools, it could be any number of different things, and then turn them back on again when there's electricity for them to use. So the loads can be used to stabilize the grid, and load management is becoming more and more popular, even to the extent of electrical panels now that have load management controls directly within the distribution panel. Changes in power systems operation. More robust substation taps if necessary, and maybe won't even be necessary with adequate storage. So anyway, these are all things that need to be looked at. And if we do it, significant reduction in generation costs, and you look at the LCOE of the sources we showed, significant reduction in water use by generation. And here's an example, but utility scale PV needs about 1.3 fluid ounces for every kilowatt hour generated, whereas anything like methane turbines use 25 fluid ounces per kilowatt hour generated. So I gotta check that just to make sure it's not. Yeah, okay. And of course, the other benefit, of course, is it's not just carbon dioxide that comes out of fossil emissions. Way back 20, 30 years ago, folks were really concerned about acid rain with the nitrogen oxides and the sulfur oxides combining with water to produce acidic. Uh, so getting rid of these is generally considered very, very desirable. And of course, the scrubbers on the smokestacks have been around for a long, long time to get rid of the NOxes and the SOxes. So the advantage, of course, on solar and wind is there aren't any greenhouse emissions and there aren't any NOxes or SOxes. So therefore, the only sign you got your greenhouse emissions associated with solar or wind is from the construction and decommissioning. But that doesn't make them different from any other energy source because every possible energy source has greenhouse gas emission associated with their construction and decommissioning, unless they are made with completely green energy out of solar or wind. So, who's responsible for optimizing the grid performance? Excuse me, I need a little drink of water here. Well, most of the pieces of this puzzle are in place. There's the North American Electric Reliability Corporation, balancing authorities, regional entities, utilities and power poles, transmission organizations, the independent system operators, and regional transmission organizations. Whoa. All right, well, let's take a look at these, okay? This is some of the control overhead, you might call it, but these are people now. These are people making decisions based on information that they measure and information coming in. Now, some of these decisions are now being turned over to smart management systems, but they've all been created by people and by these various groups. So what do they do? And of course, don't forget the regulatory agencies. They're all over the place. And some would argue we don't want all these regulatory agencies. Others would argue that we are lucky we have them. So we won't get into that. We'll just talk about what they do. Okay, so here we have the North American Electric Reliability Corporation. Okay. And what these are is these are regional groups such that, for example, in the Western interconnection there, we've got all the Western states plus two of the Western Canadian provinces, plus a little bit of Mexico down the corner there, that they talk to each other. And maybe Idaho says, oh my goodness, we've got more electricity than we know what to do with from the hydro plant we've got over there in eastern Idaho or wherever it might be, and who'd like to buy it? And so this goes up into the air to, well, gosh, we could use a little bit here in Portland. Why don't you send it to us, and so forth. So those kind of conversations that go on. Here's the acronyms. Here's what they stand for. And so we've got Western, Texas, Midwest. Notice Texas down there by itself. I mentioned that because, a couple of years ago, Texas got into some trouble when it got really cold one winter. And the problem was they didn't have enough interconnections to borrow some electricity from someplace else. And some of their wind machines were down for maintenance, and they just had a little problem meeting the electrical demand. So that's why folks are trying not to. And of course, the Florida being off there by itself, uh, well, I'm not sure we ought to be doing that either. We do have, we do buy energy from Georgia, but Florida does have its own reliability coordinating council. So this is one of the parts, okay? And it's Federal Energy Regulatory Commission that regulates the interstate sale of the electricity. So the NERC authority comes from the FERC, okay? And all these different entities out here are under the control of Federal Energy Regulatory Commission, if it's still there, presumably not. Well, anyway, that's another story. They do have a job of coordinating all this stuff. Balancing authorities, what are they? Well, they're responsible for balancing between load and generation, make sure that the people who want to buy the electricity get it, and that they get it at a reasonable price, and that the generation is there. So they look ahead and say, what's the weather going to be tomorrow? And what generators need to be running for the anticipated load. And these folks can generally estimate the load depending on the weather report and what day of the week it is by roughly 2%. So they pretty much know what needs to be on and running and ready to back up. And they need to maintain the line frequency, keep that at 60 hertz. That starts dropping, that starts meaning that they're getting overloaded, and we got to fix that. They need to maintain ties to adjacent balancing authorities, because if we've got a little extra electricity that we can share at a good price and another balancing authority, then we want to be able to transmit that over to somebody who needs it. And so the balancing authorities do that balancing act. The generation schedules to meet demand of a balancing authority area. They can pretty much predict how much generation is going to be needed based on the weather conditions. And they know where all the generators are. They know which ones are most efficient. And so they do their best to line up what has to be on and when it has to be on in order to meet that demand. Import or export, whatever is most economical, what's best for the consumer, what's best for the system in terms of not overloading the transmission lines. And so it's all an optimization exercise, basically. And as we mentioned earlier, schedule the generation to minimize generation cost. What about the regional entities? What are they? Well, they're shown on the NERC map. We saw them all. And I'm sure you've all memorized what all these acronyms stand for. And they're responsible for improving the reliability of the bulk power system. Okay, so they need to make sure that everything that's there to generate power is ready to go when it's needed. And some regions are different from others. Some need to know and get their, some planning is based on half-hour increments. Some planning is 1 hour increments is good enough, depending on how active the region is. So in any case, all segments of the electric industry belong to the regional entities, and they all contribute. Okay, we'll do this, we'll do that, you do this, you do that, and we'll all work together happily, and we'll all live happily ever after. Story goes something like that. So they account for all the electricity in the United States, Canada, and part of the Baja, California, North Mexico. And so these regional entities are out there all over the place. And there's a lot of sharing goes on between the United States, Canada, Mexico. Those in the Northeast are well aware of a lot of hydro that comes in from Canada and results in relatively clean electricity being used up in the Northeast. So, what about utilities and power pools? Where do they come in? Well, in 1935, there was a Federal Power Act, and in 1992, there was an Energy Policy Act by the federal government. And these were designed to provide reliable electricity at minimum cost. This is back when people realized that, geez, whiz, the people on the farms, they're providing us with all our food. They shouldn't have to pay more for electricity than we do, or else we're going to have to pay more for food. So let's make sure they get their electricity. So we had the Rural Electrification Act and so on. I'm old enough to remember when they were still working on implementing that back in the 1940s and 50s. Well, I guess I really didn't realize what it was all about when I was less than 10 years old in the 1940s, but in the 60s and the 50s, it started gain a little as we heard about it at a northern Minnesota rural cabin. But in any case, these utilities have been regulated to make sure that their rates are reasonable and fair. So the members of these power pools, of the investor-owned utilities, the municipal utilities, the co-ops, and the federal and state guys, the TVA people, the Bonneville Power Administration, so forth, the people who make all that hydro. Not very many private hydro power people out there. Most of those big federal dams that do that. There's power pools in Pennsylvania, in some areas that they were organized to cut costs through exchanges across regional networks. And they've been pretty successful with that. So, what are the regulatory constraints? Well, most of the system planning before 1990 was done by the investor-owned utilities. They were almost completely vertically integrated from generation to consumption. But then in 1992, the Energy Policy Act required open access to transmission because there were some folks who wanted to make some electricity and sell it to the utilities. They didn't care about distributing or anything else. They just wanted to make electricity. And that would apply, for example, to the people who, the phosphate miners who had to burn sulfur to make sulfuric acid for use in getting sulfate out of sulfate mines and for fertilizer. And in order to do that, that's very exothermic. So they had all that waste heat. They wanted to make some electricity, but that was seasonal. So that was interesting how the arrangement, well, that wasn't as seasonal. But then there were the people burning the bagasse from the sugar cane, and that was seasonal. So it was convenient that they could burn it to make electricity while the utilities could then have other generation facilities down for maintenance. So anyway, these are the kind of things that they started thinking about. How do we cooperate to make sure that we can comply with this act? And then FERC, Federal Energy the FERC orders 888 and 889 in 1996 kind of laid the groundwork for how to do this. And there was 888 that said transmission service don't have to be included in the sale and marketing of electricity. And then 2009, the American, what's that called again? Research and Recovery Act. I forgot what one of those R's stands for, the ARRA. But anyway, that's back when we had that fairly significant recession. The Department of Energy initiated a wide transmission planning and interconnection wide transmission planning. And FERC Order 1000 in 2011 was also. So this is some of the stuff that's going on and it's out there now. So we have it. These people are ready to go and are in fact in action working on the whole issue of here we're talking about some more about the RTOs and the independent system operators and so forth. And the idea being that these people are here to make sure that people get their electricity when they need it at a reasonable price reliably. And in addition now, in order to achieve this goal, all of these organizations that are in place now are looking at, okay, how do we integrate these variable renewable sources into the system? Notice this is a fair amount of government involvement at a lot of levels, from the federal all the way down to local level. So if we look at the independent system operators and in the regional transmission organizations, these are they're shown on this map here. And notice California, they kind of want their own deal. The Midwest people, but not everybody is involved with the independent system operators. Okay. These other states, they're content with the organizations other than these that are laid in on top of them, of the other organizations. Now, how do we keep the grid reliable? Well, first of all, in order to know whether it's reliable, we need a definition. And of course, it's defined as meeting customer end-use needs, even when there's reduced system availability. Okay, so it's not meeting customer needs under ideal conditions. It's basically meeting customer needs all the time. Of course, that's not practical. We know that doesn't happen. So what does meeting customer needs even when reduced system available, what does it really mean? We need some parameters here to define that. So adequacy and security. Well, what's adequacy? Well, that's the ability of an electric system to supply the aggregate electrical demand and energy requirements of the, you can read this. I don't need to read that to you. But the important thing to notice here is that supply the needs at all times, taking into account scheduled and even reasonably unexpected outages of system elements. In other words, during ice storm time, during hurricane time, utilities have to be thinking about what might happen and how do we overcome that as quickly as we possibly can. And one, of course, is that down here in Florida, hurricane season, the parking lot north end of the university in town here, whenever there's a hurricane warning, that parking lot fills up with utility trucks that are ready to be dispatched and get out there and clean up the mess if in case any of the utility lines go down and they need to be fixed. So that's kind of defined, that's part of this adequacy, the ability to respond as quickly as possible, get back in business as quickly as possible. And this includes sometimes going to work on a problem, even in another state or another area. There are agreements that we'll send our people up there to help you guys. And security, the ability of electric system to withstand sudden disturbances, such as short circuits, unanticipated loss of power system elements, and let's also don't forget about cybersecurity, because that now is becoming even more important. The more cyber it becomes, the more the more sharing of information about load management and so forth. It goes back and forth and turning things on, turning things off, systems talking to each other and so forth. So security is the ability of a system to withstand somebody trying to mess with it, whether it's a person or whether it's a natural event. Grid stability? Well, that sounds pretty obvious too. Main equilibrium in between generation and demand during normal or abnormal conditions or disturbances. You still, even if you have abnormal conditions, you are expected to be able to maintain grid stability. So that makes it more fun. System planning and operation requires all areas of an interconnection to operate within specified voltage and frequency limits. Well, sure, that makes pretty good sense. Because once voltage starts going too high or too low, or the frequency starts going up or down, you start suspecting that either you've lost load or you have too much load and you need to deal with that. So frequency and voltage are pretty good indicators of the need to find out why they're changing and what do you need to do to fix it. Generation transmission equipment has to operate within normal limits, which means that if you have a rotating machine, it takes it a while to get it up to its rotating speed, whether it's 1800 RPMs or whatever, 1200 RPMs. And it has to be really, really not just that number of RPMs, but the phase has to be exactly even with what's out there in the grid before you turn it on. Otherwise, you get a big jolt with the thing trying to lock in to be synchronized. So that's why it takes a while to get things going again. Once you lose some generation, is getting the rest of the generation synchronized. Now that's with rotating generators. One thing about the generation, for example, with photovoltaics, with inverters, the inverters can synchronize with the grid almost instantaneously within milliseconds, rather than within seconds. So actually, some of the unpredictability, there is also some predictability in the renewable sources that is not there in the rotating sources. And the predictability is that the non-rotating sources, the electronic inverters, can instantaneously get up to speed and synchronize with the utility. So let's talk a little about planning reserve and reserve margin. Start with the definition, additional. What's the reserve margin? It's the additional capacity above and beyond the expected peak, so sufficient resources are available at all times to meet peak demand. Maybe that's about 20%. That means you're going to have some spinning reserves. You're going to have something out there that is ready to come on when it's needed during an anticipated peak demand. And not only that, but if you lose some generation somewhere for whatever reason, you need some additional capacity elsewhere to be able to take over for the generation that gets lost. Okay. So now we get some more wonderful acronyms, and I hope you all memorize all these acronyms. I love these, the LOLLIP and the LOLLI. And the LOLLIP is the loss of load probability, and LOLLI is the loss of load expectation. Now, what in the world are those things? Well, we're going to see a picture and we'll get an idea of what they are. The whole target for a loss of load expectation is 1 day in 10 years, or a tenth of a day per year. Okay, which the tenth of a day is 2.0, or no, it's 8,760 hours in a year. So in terms of hours, 1 day would be 24 hours in a year. And so we don't want more than 24 hours a year of outage. If we have a 1 day in 10 year, I'm sorry, we don't want any more than 2.4 hours a day outage for any 1 year if we're going to have a whole day in 10 years. Okay, my mistake. 2.4 hours a day, or that's effectively means 2.4 hours in 1 year, which would be 24 hours in 10 years. That's a day. okay? That's the allowed loss of load expectation, and utilities endeavor to achieve that, okay? So how do you do that? Well, first of all, we define the effective load carrying capacity. And what that is after you add new generation with a consistent loss of load or constant loss of load expectation, how much additional load can you supply as a result of adding some new load? And this sounds complicated, but it's simplified if we look at a nice picture. So let's take a look at the picture. If the target is 1 day and 1 year for the lolly, all right, that's 0.1 day in 1 year. Then let's say we have the existing generation represented by the blue line. And let's say the existing generation is generating at 8 gigawatts, which is below its full capacity. Then it turns out the lolly is about 0.062, doesn't it? Or 0.063, somewhere in that neighborhood. And notice that as you increase the load on that generation, the likelihood that it's going to go down increases. So as we get up to 10 gigawatts, we reach the lolly maximum. So if we want to maintain that maximum 0.1 day per year, for loads in excess of 10 gigawatts, we're going to have to add some additional generation to the system. But the question is, if we want to add another 0.5 gigawatts, do we have to add 500 megawatts to get that? And what we're looking here is we're adding 400 megawatts. We want to add 400 megawatts extra and still maintain that lolly. And so can we do that with 400 megawatts? And the answer is no, we can't do that with 400 megawatts. It turns out that just the difference in additional generation is more like 750 to 800 megawatts. So you need almost twice as much actual generation capacity in order to achieve that 1 day in 10-year loss of load expectation. So you can't just add this load linear, you have to add about twice as much in order to maintain the reliability. And that's important to know because this is part of the planning process. All right, so what does a typical utility load profile look like? Well, it depends where you live, whether you're north, south. The red line, this is kind of a southern profile, but also a relatively reasonable northern profile. But in the winter, in the north, there's generally a peak somewhere between 6 and 10 in the morning where electricity is needed for heating and keeping people warm. So bigger peaks in the morning. And of course, this peak is not, notice there's no scale on the left-hand side because this is the vertical scale. This is a relative peak that goes up and down. In spring and fall, it's not as high as it is in the summer. It's generally the highest during the air conditioning season, and somewhere between the spring and fall in the winter during the heating season. But every utility in every region has its own utility load profile, and it's needed in order to know what kind of generation is needed. So let's talk about characteristics of generators. Base load generation takes longer to ramp up to a maximum output and it likes a more constant load. We talked about that before. And whatever that base load is. And the reason is because it's big. Nuclear plant, 500 megawatt nuclear plant, for example. It can easily take it up to 1 or 2 days to get that thing up and stabilized. A lot of heat, a lot of inertia, a lot of heat inertia, a lot of mechanical inertia, a lot of inertia period that needs to be stabilized. All right, so once you got base load going, you like to kind of keep it going. And so it's very useful again, to know what the base load is on these loads, and we just saw what the base load was in that previous curve. Now, base load generation is that's the least expensive, and most of the time it's been thermal, coal, natural gas, and nuclear. Long ago, before the oil embargo in 1974, there's a lot of oil being burned. Crude oil. We've had some very large crude oil plants here in Florida, and it took the utilities a few years to convert over to burning natural gas instead of crude oil in those. So there's almost no crude oil now being burned at the utility scale, except for certain, there's some diesel systems in the megawatt range, generators that will burn diesel fuel. But even in the kilowatt range, the 15 kW type range, most of the generators are natural gas now. So in that case, and once again, they're based on expense, and it's usually been thermal. So some of these plants, the natural gas plants in particular, can follow the load on an hour-by-hour basis. You crank it up, and everybody knows when you've got a gasoline generator, if it's rated at, say, 5,000 watts, that 5,000 watt generator is perfectly happy to light up a 100-watt light bulb, because as long as it's cranking out at 120 volts, 60 hertz, the amount of current it delivers, it's perfectly happy to just run at 120 volts and 60 hertz and not deliver any current whatsoever. The only penalty you pay is it burns the gas and you pay for it. So as a result, the rotating generators that are fossil fuel, they're most efficient at somewhere around 80% of their peak load. And of course, when you come closer to peak load, they burn more gas because burn more fuel, because obviously the energy out has to be less than the energy in. There's some thing about a second law of thermodynamics that requires that. So, but when the energy out is zero, that is in fact less than the energy in if it's more than zero, and 0% efficiency. And it's not desirable to run a big generator to run a 100-watt light bulb, because it's just not very efficient. So maybe it's better to run that 100-watt generator charge battery for a short time, let the battery run the 100-watt light bulb, and then turn the generator on again. So we get into the storage issue. In any case, if a generator can meet the changing load, it's going to depend on the time it takes to get to synchronous output frequency. Once again, we mentioned that earlier. And certain generators can get there faster than others. The bigger the generator, generally the more efficient. And what we're looking at here is how many kilowatt hours you can get out of a gallon of fuel if we're using a gasoline generator, for a generator up from between, say, 300 watts up to 100 kilowatts. Notice the log scale on the horizontal axis and the linear scale on the vertical axis. So in general, larger generators are more efficient. There's less heat loss, and more of the energy is converted into rotating mechanical energy. On the other hand, take an electronic inverter, and the efficiency versus power curve looks more like this. And this one goes up to 95%, but in fact, this would be an inverter that has a transformer in it, which has fairly significant losses. If you have the transformerless inverters, which most of the inverters now are, the efficiency of the curve is going to go up to 98%. And why does it drop off as you go up to higher output ratings? Well, it drops off simply because you still have electronic components get warm, and you have I squared R resistance losses as you start pumping out more electricity. But notice these units, they peak out at somewhere near, oh, say 20% of their maximum operating capacity. But even when they get out to maximum operating capacity, they haven't lost very much efficiency. It's where they lose their efficiency that if, again, it's just like the other sources, at very low loads, the efficiency of the inverter goes down. All right, so it's useful to know that. And of course, the inverter, electronic inverter, can get up to speed in a matter of a few milliseconds if you want it to, or it can be set to ramp up a little bit slower. There are different reasons, different cases. If you lose a generation source, you want to get another source to replace it as quickly as possible. And there are examples of a 100-megawatt system in Australia recovering in a matter of 100 milliseconds or so once when a coal-fired plant was lost back in 2017 or 2018, I think it was early 2018. So in any case, inverters can be very, very handy when you lose a conventional generation source, or even if you lose an inverter source, another inverter can come on pretty fast. Now, this also applies to battery storage, because the battery storage, of course, is DC, and the battery has to have an inverter in order to tie in and provide AC. But this whole matter of milliseconds to connect applies to batteries then as well, because they connect to the grid by way of an electronic inverter. So batteries can be very helpful if you want to keep the grid stable, because they can connect and they can deliver whatever the grid wants it to deliver very quickly. So, whoops, we did that one. I pressed my finger the wrong direction on my mouse. So basically, an inverter is an uninterruptible power source. I have sat in a house with a battery backup system, solar, when somebody switched off the grid for a moment to see what would happen, and you don't even notice the lights flicker. The inverter picks up so fast to pick up this backup, so you can barely see the lights flicker. It's just that fast. So what is a security constrained unit commitment? More acronyms. I'm sure everybody is clapping and cheering because we've had what now, 200, 300 acronyms today? Quite a few. All right, so let's take a look here. Well, it's generated, that's committed 24 to 48 hours ahead of time. All right, so that means that if you've got a big thermal unit that you want to have available tomorrow or the next day, you might have to start it up now in order to get it up to speed so that it can lock in and synchronize in a relatively short time if it's needed. Okay. The load forecast accuracy I mentioned earlier is about 2%, so that means that you can have these things ready uh, as long as the forecast accuracy for the next day is about 2%. What if you have too much? Well, if you got too much, that's pretty inefficient because you have something running without delivering anything to the grid. And if you have too little, then if something happens, it means your grid can go down. So uh, you need to be careful and try to hit it just right. And if you don't want to have too much expensive peaking equipment, because peaking equipment is more expensive in terms of the initial cost and also the fuel cost of peaking equipment can run up into somewhere between the 10 to 20 cent a kilowatt hour range, which is one other reason why peaking electricity is very expensive. Not just because of the fraction of time that it operates, or the compared to 24 hours a day, but also to the higher fuel cost. So peaking electricity, I've seen some cases where a really pinch, the peak value of electricity goes up to as high as $2. And that really surprised me. I thought I was looking at 50 cents or so, but the worst time of the year when they're cranking out everything they possibly have to crank out, that cost of that peak electricity goes up to somewhere around $2 sometimes. Every day, balancing authority schedules which generation within its authority is turned on and whether it's used to provide energy, power, or whether it's there as backup. But that's where the balancing authorities come in to make sure that these things are ready to go if necessary. So what about operating reserves? There are classifications, of course. What might be the situations be? Contingency reserves, all right, and that's the NERC people require that. North America, the energy reliability. Why can't I remember these acronyms? There's only a couple hundred of them. Anyway, Reliability Corporation, okay. So you need these contingency reserves, but that's not all you need. You need to have non-event based reserves. Non-event based reserve? What in the world is that? Well, those are used to manage short-term fluctuations in demand, as well as load following reserves. So yeah, there are short-term fluctuations in demand. Maybe like about a certain time of day, a certain factory will close down, and the factory uses a lot of electricity, and they turn off all their lights, or they turn off all their manufacturing and motors or whatever they're using that use electricity, and maybe you drop by a megawatt or so. Well, you need to be able to make sure that you're not generating too much electricity then. But what if they start up? Or what if they had to shut down and start back up again? You need to be prepared for that. So you don't just follow the load, but when you have unexpected things turning on and off, you need to be ready for that as well. Regulatory reserves, frequency control reserves. If you're going to be frequency control, they have to be spinning, and they have to be spinning at exactly the 1800 RPMs, or whatever frequency it takes, depending whether they're 2-pole, 4-pole, 6-pole type machines, so that they will come out with exactly 60 hertz electricity. Now, there's interesting spinning machines that can do that aren't even motors, but if you have a flywheel and you get it up to a high speed, that can provide a very reliable frequency control reserve. And if that flywheel is driving an inverter, then that inverter can be even more reliable frequency control reserve. So interesting stuff there. Loss of generations detected by system frequency decrease. Okay, that's understood, because all of a sudden everybody else has to work harder, and when you have to work harder, a generator slows down instantly until they are able to hopefully eat a little bit more fuel and get their speed back up. But during that moment, there's going to be a drop in frequency, and that's where, if the existing generation can't manage it, something else has to come on and help out. So, but here's an example of what the picture might look like if you lose a large generator. Then the governor response is going to be, we're going to apply more gas and try to speed this thing up. But then we need to not just do that, but if we have to throw more generation in order to get up to speed, then the AJC response comes in. But in any case, within right here, you see within about 6 minutes, we're back up to normal frequency. And this is a typical contingency response, is within 6 minutes they're up to frequency. The grid never did shut down because you see it only went down by 1/10 of a hertz, but that 1/10 of a hertz is enough to get things that other pieces of equipment to get their attention, so they turn on and make up for it. And this, like I was saying, the flywheel is a very helpful piece of equipment to get rid of these glitches. Generator inertia itself, these are big pieces of steel rotating. So the generator itself, you notice that line where it drops. Yeah, that implication is the thing was going at full speed and it dropped off and it shut down to 0 in about 30 seconds or so. But it didn't instantaneously shut down. It took about 30 seconds. And so when that happens, the governors on the other machines recognize that and they try to pick up to meet it. So what are we reserving? NREL says new transmission could address the general increase in grid congestion. Okay, that's important. So we're going to need some new transmission. Again, we're talking, what do we need to do to take care of any issues we might have with variable issues from either the loads themselves or from the generation as we add more variable renewables to the grid. So when photovoltaics is peaking in the west, you can send electricity to the east, and that's good. So it doesn't hurt to study the economics of increasing west-east transmission capacity. And at this point, somebody's undoubtedly studying whether to do that, because then they'll figure out how much they have to charge for that electricity in order to pay for the transmission line. And that's the kind of thing that Wall Street loves to do. And you can bet that somebody's making that study right now and thinking about where they might put that transmission line. Speaking of transmission, there's two different kinds, AC and DC. And it's interesting to compare the cost. And here's a couple of different situations. It's a matter of how long is this transmission going to be? Whether it's 255, 750, or 1,000 miles long, how many dollars per megawatt hour transmitted? And of course, the longer it gets, the more expensive it gets for transmitting that megawatt hour. But look at that light blue line at the beginning. That's for the low voltage transmission, where it gets a whole lot more expensive for longer distances. And why is that? That's because there's more losses. Because our lower voltage is higher current, higher I squared R losses. So you want to transmit your electricity at the highest possible voltage. So now look at the one, that dark blue. That's 800 volt, 800,000 volt, high voltage DC. Now, why is DC less expensive than AC? And the answer for that is because this thing called a skin effect. With AC, most of the electric current flow, stays within 1/4 of an inch of the surface of the wire. And the center of that wire has very little current flowing. And therefore, the bigger they make the wire, it's still only going to keep that electricity within about the outer 1/4 of an inch. Do this thing, it's a magnetic effect. And it only works with AC. With DC, you use the entire cross-sectional area of the wire at the same rate of flow throughout the wire. Now, DC, you have to make it at the beginning, so that costs some money. And you have to convert to AC at the other end of the line, so that costs some money. So that's why the longer the distance, you have that fixed cost at the beginning and the end of the line. But then the cost of the line itself, the losses, increase significantly slower for a DC line than for an AC line. And you see right here, for a 1,000-mile line, and even for a 500-mile line. 500-mile line is where it really is a good idea to run one of these. So somewhere 300 to 600 miles, and beyond 600 miles, forget about it. You don't want to run a AC transmission line that long. You want to do DC. The footprint too, even, is important on transmission line. And look at that one in the lower right-hand corner versus the upper left. You got 5,000 megawatts on a 345,000 volts, 6-circuit AC is 900-foot right away with 90-foot towers. Here we've got a 145-foot tower with 800,000 volts DC, has a 270-foot right away. So less than a third of the right of way necessary for that big DC. And in fact, that's carrying 6,000 megawatts instead of 5,000 megawatts. So again, cost of land, right away, and so and all that. So DC is the way to go when you're having long distance. So we'll be seeing more of this. Chinese are building these like there's no tomorrow. They've built quite a few in the last few years. And you can see that what these are. We're 5,000 megawatts at 500,000 volts. Then we go up to 6,000 megawatts at either 765,000 volts AC or somewhere between 500 and 800,000 volts DC. And notice again, right away, 600 feet for those 3 towers on the AC, 135-foot height. And the DC, half of that right away, and only slightly taller, get those lines up off the ground for safety purposes. This is an interesting line that I happened to come across while traveling in Newfoundland a few years back, around 2018, I guess it was. Noticed this power line alongside the road and came back and looked it up, and sure enough, here's this line going from up there, a big hydro plant up in Labrador. Part of it goes underwater up at that top northern peak of Newfoundland, goes all the way over to the capital of Newfoundland and St. John's. It's 1,100 kilometers, and 4 of those are in New Labrador and 700 in Newfoundland. It's overhead plus underwater. You can see where it goes underwater up there in the bay. And 900 megawatts, 350,000 volts. So it's not even that high, super high voltage, 350 kV. So it doesn't have to be quite as high on the towers. And that's what it looks like. Now it's side by side. Notice the towers in the back, the lower towers. So those are 3-phase AC transmission, and these bigger, taller in the foreground are the DC transmission line. And you say, oh, that really messed up the terrain. Well, picture was taken less than a year after the line was commissioned. If you look back to the AC lines, you notice the trees are growing again. And for the most part, this natural landscape is going to return where these towers are. So anyways, if you haven't been out to look at a DC transmission line, this is at least an approximation, gives you a little view of it. And they're pretty impressive. You see it from the road and immediately you want to turn off and take a look and see what that thing is and take a picture. But just in case in another couple of years you might be doing webinar and you want to show somebody your pictures. So in any case, look what's going on in China. 1,000 kilovolts, 6,000 megawatts. This is a ultra high voltage AC. If you get up to 1,000 kilovolts or megavolt with AC, the higher the voltage, the less the current, the lower the losses. But then we look at plus or minus 800,000 volts. That means that the plus line is 800,000 volts above ground potential, and the minus line is 800,000. So that's 1.6 megavolt, 5,000 megawatts. And this thing goes for 1,438 kilometers. That's a big system. Here's another 800 kV, 6,400 megawatts for 1,907 kilometers. So the advantage, decline in per unit cost, but of course there's disadvantage and a risk. If you lose that line, you are losing a lot of power. And so you got to make sure you build these things so they are really, really rugged and no way that they're going to fall down. So how do we meet this 80% challenge? Now that we've got all this background, let's take a look. Technical challenge, dispatchable, predictably available for planning ahead. So here's some of the renewable sources that are dispatchable. Hydro, yeah, that's predictable. Geothermal, pretty predictable. Concentrated solar power with thermal storage is pretty predictable and dispatchable because you're heating up a salt such that it is then available for thermal generation at night. So that's predictable, and bioenergy is pretty predictable. Okay. So there's some renewable sources. I'm sorry, I don't know if you're hearing the background phone call, but I'm going to go close the door. Okay. I noticed that usually these things filter out jackhammers pretty well, but voices in the background sometimes are a problem. So I just want to make sure that have a sufficiently quiet background. So here are some dispatchable renewable resources. So those are fine. We don't have to worry so much. They're a lot like our existing conventional resources. Whoops, went the wrong way. But wind and solar photovoltaics are not completely dispatchable. But to some extent, they're partially dispatchable because wind is kind of predictable. Okay. And if it's predictable, then it can become more dispatchable. And but still, we do have variability and uncertainty of when the sun is going to shine, and when a cloud is going to come over the sun, when the wind is going to stop blowing or whatever. So we need to deal with that. And there's more known. They've done more studies on wind uncertainty than they've done on PV uncertainty. I've done some simulations myself, and I have. I'm pretty well convinced myself that PV uncertainty is pretty much a lot like wind uncertainty. So we can take a look at the wind. They both have less variation if they're aggregated over a large footprint. If we had 100,000 photovoltaic systems in South Florida within 50 miles of each other, they would have far less variability during the day due to cloud cover than 1 or 2 or 10, simply because everybody's not cloudy at the same time, unless it's totally clouded over, and then there's no variability. So that solves that problem. Also, if it's totally clouded over, then there's not quite as much air conditioning demand, so that kind of helps. So in any case, a bigger footprint is advantageous. Photovoltaic output varies more than wind output. Even if the wind slows down a little bit, there's some inertia in the PV, but if a cloud comes over, I'm sorry, there's still some inertia in the wind, but if a cloud comes over the PV, Well, the, the brightness of the sun drops down. You could lose 50, 60, 70% of your output, depending on how heavy that cloud might be. And you could lose it within less than a minute. So that's something needs to be dealt with. If PV is installed at the distribution level, it can challenge the management of distribution voltages. We talked about that a little bit earlier about how if you start sending power backwards on the distribution line, it can actually increase the level of the distribution voltage. So that's something you want to manage one way or another. And then, of course, that's going to be a part of the role of the substation is to be monitoring that. And if there's a proper control system, it will send information out to storage systems along the line saying, hey, you got to absorb some of this electricity right now because we don't need it right now. So please save it until we need it later on. Now, the concentrating solar power with thermal storage, that can ride through a solar variations up to 6 hours. So that's not a problem. Um, It all depends on how much storage they've got. So in other words, the concentrating solar is you're making hot water essentially, and then we're using that hot water for steam. And it's not hot water though, it's hot molten, sometimes sodium, for example, something you can get up to maybe 800 degrees or so. And that can carry a fair amount of heat if it's got sufficiently high specific heat. Okay, and they're doing a lot of experimentation with this out west. Solar, photovoltaic, or wind with storage can also ride through variations depending on the storage levels. And this is where we're seeing an incredible amount of activity right now out there. Very, very large storage systems are being developed by the utilities. We have, I think, the second largest in the country, I believe we have here in North Florida. Something in the order of 300 megawatts or so. It is available in almost an instant of time from the storage battery if the utility needs it. So storage is the key, and it is happening like crazy right now. So how can flexible technology solutions be enabled? Well, the demonstration of technical principles, that's only the beginning of it because you have to not do a whole lot more than just demonstrate it. Uh, there's been a lot of work done on the wind, so therefore we know what these principles are. And then we have to look at the institutional impacts of all these other guys. And that can be pretty complex. So just so you this is because you demonstrate that it works. That doesn't solve the problem. You got to prove it works by demonstrating that it works over a relatively long period of time before people start believing it. Fortunately, this is happening right now and it is working and people are starting to believe it. 2012, though, that wasn't the case. But now in 2025, we've got some systems that have been out there for quite a while and they are proving themselves beyond wildest expectations. Maybe that's a little bit much, but they are definitely proving themselves. Things like there's a system, utility storage system up in North Carolina that's built with used storage batteries from electric vehicles, from hybrids and others, because an electric vehicle needs to be able to have instantaneous response with a storage thing. It has to have very low internal resistance in a battery, but the utility doesn't require the same level of performance out of a battery. So these lithium batteries that are in vehicles are now being when they're replaced, they don't take them apart or throw them away. They just transfer them and they use them as storage at a utility site for another 10 years or so. So, but then again, there's the institutional challenges, and it, they're less studied. And I put this, ask any photovoltaic installer, because we're talking about the inspectors and we're talking about the authority having jurisdiction and the plan reviewers and so forth. And in my spare time, rather than being bored as a retired person, I've been reviewing plans for photovoltaic systems for the last 4 years. And I can tell you that the most challenging thing is not designing it, but convincing the building department that it really is going to work and it really is not going to blow away and it is going to be safe. And that takes a little work. And that's why I have a little thing about Ask Any PV installer. But it's well established that these things work just fine. Here's a wind generation, interesting example here, because it shows that when there's wind power available, and that's the red graph on the bottom, and you see how, now this is an hourly variation thing, so we're not having variations by the second or the minute, but we're looking at variations by the hour. And then we're looking at what is the load, that's the green one. And so that's the load that has to be met by the generation. So what you have to do is add up the red plus the blue, and that gives you the green. Now, notice that when the red drops off, well, first notice the slopes on the green graph up there. And they're, well, they're maybe challenging, but they're relatively low. And now take a look at some of the slopes on the blue graph. Look at the red slopes where it goes down there between 50 and 60 hours. It goes from, 5,000 down to nothing in terms of megawatts almost. And as a result, the net load, the rest of the backup, has to increase pretty fast over that time. So that's a lot faster than it had to increase without the wind. So something is needed to either the conventional generation has to do that, or if we add some storage, then it can take some of this effect away from the rapid adjustment of the conventional generation to take care of that fall off of the wind. And in the meantime, then all of the area under that red curve is energy, which does not have to reduce by the non-renewable sources. So it's worth looking at how to make sure that everybody, all of these can work together in harmony. So here's an interesting question. What happens if the net load goes negative? In other words, if the wind generation, if that blue load went down negative, if the red curve went positive. And of course, that's even more interesting, because that's the thing we talked about earlier, where you don't want the conventional rotating generation to be forced to rotate backwards. So again, if that happens, you want to remove energy from the grid and dump it into a storage facility to make sure that it doesn't try to run the conventional rotating generation backwards. Recent analyses, 30% wind generation over large footprint has been analyzed, and 5% solar has been analyzed. And here's what we got. Studies in a long time ago now, almost 20 years ago, but the wind blows about the same and the sun shines about the same. These are wind. And notice that as you have more wind power, lower left, we're in 15,000 megawatts now versus 1,500 megawatts. So we're 1,000, from 100 to 1,000, 10 times more wind in the bottom than on the top. And look at how that curve is much closer to a straight line of, now this is deviation from the predicted value. Okay, so, and again, the other study that was done in Colorado versus New Mexico, same kind of thing. Here we've got a significantly bigger wind power on the lower right-hand side, 30,000 megawatts versus 400 megawatts, and 40,000 megawatts. No, I guess that's, yeah, that's more. Okay, so an even bigger, but similar situation where the more you have and the more diffuse it is, the more dispersed it is, the more constant, the less variability in the generation. But there's still variability, and that still has to be dealt with, but not as much. Okay, and these are 1 hour changes in wind power. Solar, probably 1 minute intervals would be more important to look at. The amount of time it takes a cloud to obscure a photovoltaic system. And but I'm convinced that the graphs would look very similar as soon as this study comes out, and I can't wait till it does. Tracking on PV is something that can be done. The array you see on the left there is a fixed array looking south, and the one on the right is it's a tracking array, but it looks, right now it's facing northwest, and in the morning it's facing southeast, so it flips over and looking in the other way, like looking away as you look at your screen. And then as the sun works its way across the sky, it effectively, the more direct the sunlight impinges on the solar panels, the more electricity it makes. So therefore, rather than having a sort of like a normal curve on a nice bright and sunny day, this normal curve has a bigger standard deviation in hours than it would have for the fixed array. It has a bigger standard deviation for the tracking array, and the tracking array will then probably also produce about 20% more electricity, more kilowatt hours. So, so what it means is tracking improves the dispatchability a bit if you have tracking arrays, and some reasons where you might very well want to have tracking from southeast to northwest. Because after all, southeast facing is where the sun is going to be on a cold winter morning where you might like some extra electricity. And northwest facing is where the sun is going to be on a hot summer afternoon where you might want some extra electricity. So southeast and northwest is not an unreasonable way of tracking. Okay, what about financial impact? Well, General Electric studied this. We're getting close to the end here, but we're close to being done. So that's consistent. Savings, if you have good forecasting. Okay, and so forecasting is important. And once again, forecasting, very important. It shows the benefit of $4.37 a megawatt hour for good forecasting. Because it tells you how you need to back it up and what you're going to back it up with. Pricing. Some generation has capital, operating, and fuel costs and disposal costs or decommissioning. And others has no fuel costs. So if you don't have a fuel cost, you want to run that thing all day long because that's how you get the most benefit out of it. Even if you have a fuel cost, you probably want to run it all day long. But if you have the choice between running something with fuel and running something without fuel, anyway, it makes it more complicated in doing the analysis. It's interesting to think about that. No fuel, operating costs a lot less because the maintenance is very minimal when you don't have to replace the bearings and change the oil and whatever else you might have to do. Most thermal and variable sources, the capital costs are about the same, but the variable sources simply don't have a fuel cost. So that gives them a big advantage. And so therefore you justify the thermal units because they need to back up the variable units. Well, that's true except when we replace the thermal units with storage. And so that's the question. And back in 2012, this was the questions they were asking, but now we have the answer that no, we have the storage technology now available to replace the thermal units with storage enough such that minimal thermal units will be necessary, and likely those units will be the nuclear plants as opposed to the fossil plants. Because new nuclear plants, although their cost is pretty high, operating an existing and maintaining an existing nuclear plant is still a relatively cost-efficient operation. Flexible load examples, charging and charging an electric vehicle. Aluminum, you can shut it down if you have to during peak time. Thermal storage, cold or hot, smart grids. Turns out that half of the ERCOT load is responsive. That is the maximum you can allow. But demand management is going to be big time. It's going to come even more important. So if you think about electric vehicles, a fleet of 100 million electric vehicles, each of which can deliver 5,000 watts to the grid at 4:30 in the afternoon when it's parked in the parking lot at the factory or at home or wherever it is, plugged into the charger, all charged up on solar electricity that was generated earlier in the day. That's an awful lot of storage that can give back an awful lot of kilowatts and kilowatt hours to the grid. And that's just with automobiles, not counting storage batteries in residences, businesses, and out in the field and utility size. So small thermal inverters, diesel and gas turbines can start and ramp quickly. Probably won't be very many of them. Hydropower is important. We've got a fair amount of the biggest storage right now is reverse hydro or pumped hydro, pump hot water up a hill. And the short response from hydro is about half-hour turnaround to go from pumping uphill to downhill. So energy storage, here we go. We're running short on time. I got to go a little quicker here. Here's some of the energy storage mechanisms. We see what the problems are with the other means of backing up. And it turns out that the energy storage is coming on really fast. And within the next 10 years, we're going to see an extremely, an amazing increase in energy storage by batteries. And for sure, we're going to see it in China and India and the European Union. And presumably, we're going to see it in the United States too, just because it makes such good economic sense. So we'll see what happens on that. People argue, oh, but it takes energy to make these things. But yes, when you make these things, they pay back that energy and the energy they store and avoid having to use after about 3 years. So the energy payback time on anything we're talking about here, in order to make it economical, is typically 3 years when the lifetime is 10 years or longer. So, and then of course they're all reusable or recyclable. What will it do to the grid? Well, here's what we got today. Mostly we generate in the substations, send electricity to the transformers, to the loads. and it's all one-way deal. But tomorrow and in the future, it's going to be a whole lot different because there's going to be a lot of uh, baby, and when I say baby PV and small PV and so forth, and basically we're saying you can change PV, you call it renewables, but a lot of it is going to be PV because that's just the way the market is going. And we're going to have storage at all levels, small level storage, 5 kilowatt hours, 10, 15, 20, 50 kilowatt hours residential, uh, hundreds of megawatt hours of storage on large, big renewable storage on the transmission side. So keep an eye out for this happening to the grid. And of course, along with all this fancy stuff that we see is an awful lot of fancy control stuff, much of which originates at the substation. And communication with all of the loads and all of this of the storage and all of the transmission and generation. Trying to balance them out, keep everything happy. And that's what it's all about. And the ideal energy source, what does it do? It operates efficiently, follows the load, is economical, is not subject to fluctuations in fuel price, doesn't pollute, lasts forever, and it can be developed, installed, and used by hostile countries without causing a threat to others. I've never heard anybody concerned about how much solar the Russians are installing or how much solar they're installing in any other country that might be considered hostile. It just doesn't seem to be the thing that concerns people. So anyway, that's it for the day. We did go over a little bit, but I think our host would probably allow if we have any quick conversation you might want to have, any comments. Let's see what we got. I see something in the chat box here. Let's see what that is. This is from the host, I guess. Yeah, please clear Q&A before you close. All right. Oh, here we are. Q&A. We got some. Let's see what we got. Q&A. Okay, how is switched LED switchers? Oh my goodness. Well, they're roughly 10 times more efficient than incandescent. That's the quick answer to that one. And they last a whole lot longer. The Act of 1992 allow for cogenerators sell power to the grid. Yeah. As long the act is fairly straightforward. If you want to sell power to the grid, you have to sell clean power to the grid. So let's see. And transformer. I'm not sure what you mean by transformer there, Bruce. Maybe you could be a little more specific. You mean a transformer and an inverter? Transformers at distribution or substations or XFMR, yeah, acronym transformer. Okay. All right, well, that's it. Thank you all for attending. I hope that you felt this worth your while. If you've learned something you didn't know before that you want, maybe you didn't even know you wanted to know. Um, but we're always interested in any feedback you might have, because that's the only way you make things better is to get feedback. So feel free to do an evaluation if you have a chance. We'll read it carefully. And my feedback would be next time I do this, it's going to be updated because there's new stuff going on that we could add to it. So meantime, hope everybody, if nothing else, hopefully you can apply this to a renewable license. And I guess there's a quiz you got to take here as well. And read the chat for all the rest of the answers that you need to whatever questions. And wish you all a good week and a good weekend.